Hello, my name is Tejas Srinivasan, and I will be presenting our paper, CLIMB, a continual learning benchmark for vision and language tasks. The dominant paradigm today for deploying pre-trained vision-language models on vision-language tasks is single-task fine-tuning, where you fine-tune a copy of the pre-trained model for each new task. This gets expensive as we need to store a copy of the model for every task. One solution to this is multitask learning, where a single model is fine-tuned on several tasks simultaneously. However, this is a static paradigm, as the model cannot learn new tasks that it encounters. In this work, we focus on the continual learning setting, where a model encounters a sequence of vision and language tasks. The model must use knowledge that it has learned from previous tasks to learn new ones, while not forgetting tasks that it has already learned. This is a dynamic and continually evolving paradigm which has been so far unexplored in the multimodal domain. To address this, we introduce CLIMB, the Continual Learning in Multimodality benchmark. The learning setup in CLIMB consists of two phases. The first phase is upstream continual learning of a sequence of vision and language tasks. And the second phase is downstream low-shot transfer to unseen vision and language, as well as language-only and vision-only tasks. CLIMB consists of four main components: a collection of multimodal and unimodal tasks, a set of continual learning models, a set of continual learning algorithms, and an evaluation protocol for evaluating the various properties that are desirable in a continual learning setting. In the initial release of CLIMB, we include 4 vision and language tasks, which require a diverse set of reasoning styles, as well as 5 language-only and 4 vision-only image classification tasks. The CLIMB benchmark is designed to be extensible to introduce new tasks as needed. Continual learning models in CLIMB are designed in a task-aware fashion. They consist of a pre-trained vision-language transformer, which acts as an encoder of the vision and language inputs, and task-specific output layers that make classification decisions for every task. In our experiments, we use the pre-trained VILT model as our transformer backbone. In our initial release of CLIMB, we support 6 different continual learning algorithms. Sequential fine-tuning, where the full transformer is fine-tuned along with the task-specific layers as each task is encountered. Frozen encoder, where the shared parameters, that is the encoder, are frozen and only the task-specific layers are trained. And frozen bottom K, which is a middle ground between the two, where only the bottom K layers are kept frozen. In our experiments, we set K equal to 9. We also include 3 more sophisticated continual learning algorithms: experience replay, elastic weight consolidation, and adapters. Now let's look at our evaluation protocol. We wish to evaluate 3 properties of models in the CLIMB learning setting: the ability to transfer knowledge to new tasks from previously learned upstream tasks, the ability to prevent forgetting of previous tasks, and the ability to do low-shot transfer to unseen vision language, as well as language-only and vision-only tasks. Let's look at these one by one. In upstream knowledge transfer, we evaluate the performance of the model on a task after encountering a sequence of vision language tasks before it, using the continual learning algorithm A. We benchmark this against the performance of the model on that task if it was directly trained from the pre-trained model without any of the previous tasks. In our evaluation, we compare the performance of the model against the random baseline, which is SR. The red line represents the improvement of the pre-trained model over random performance. The blue line represents the improvement of the model using continual learning algorithm A over the random performance. And the upstream knowledge transfer is measured as the relative improvement of the continual learning algorithm A over the pre-trained model, which is represented by the green line divided by the red line. In forgetting transfer, we evaluate the model's performance on a given task after learning several tasks before it. And after learning a future task, we again directly evaluate the model on the previously learned task. This is the transfer score from I to J. The forgetting transfer is measured as the relative decrease of the model's performance after training on the future task, which is represented by the green line divided by the red line. In our low-shot evaluation transfer, it is set up similarly to the upstream knowledge transfer, except that the task that we're evaluating on is a low-shot task, which is either an unseen multimodal or a unimodal task. The low-shot transfer is measured as the relative improvement of the model's performance on the low-shot task using the continual learning algorithm A compared to directly using the pre-trained model, which is again the green line divided by the red line. In our experiments, we order our upstream tasks as shown here. We use the Wilt-based continual learning model, and we evaluate our 6 different continual learning algorithms. In our upstream knowledge transfer, we observe that more continual learning tends to hurt the model's ability to learn new tasks. And we also see that methods that fine-tune more shared parameters tend to do worse in terms of decrease. We also see that the frozen encoder is not able to learn any of the tasks as well as fine-tuning the entire model. Additionally, we see that adapters do not show negative transfer, as depicted by this blue line, and do much better than sequential fine-tuning and the other continual learning algorithms. In forgetting, we evaluate the model's performance on the previous task after learning each new task. So for example, after learning task 2 over here, I evaluate the model's performance on VQA. After learning task 3 over here, I evaluate performance on task 2 and task 1. And after learning task 4, we evaluate performance on task 3, 2, and 1. We see that more fine-tuned parameters tends to lead to more forgetting, as evidenced by the forgetting of the sequential fine-tuning algorithm. Meanwhile, adapters and frozen encoder do not show any forgetting, as evidenced by the green and purple lines. We see that experience replay does better than elastic weight consolidation, and we also see that the forgetting issue tends to get worse after the visual common sense reasoning tasks. We believe that this is due to the large difference in visual domain between visual common sense reasoning and the tasks seen before it. We also evaluate the low-shot transfer to unseen vision and language tasks. The findings here are similar to the findings in the upstream knowledge transfer. We see that the low-shot transfer is always negative, as was the case with upstream knowledge transfer, which is unsurprising since if continual learning hurts the model transfer with full training data, the same is likely to be the case with in a low-shot regime. For vision-only tasks, we see that continual learning again hurts low-shot transfer, as evidenced by the downward trend of the low-shot transfer performance as we see more tasks. And we see that the NLVR task, which is task 2, and the VCR task, which is task 4, have more of a negative effect. For language-only tasks, we see that upstream continual learning sometimes helps. Here, rather than looking at the transfer scores, we look at the direct accuracies to compare our two models, Wilt and Wilt-BERT, which is Wilt using pre-trained BERT representations instead of the Wilt language embeddings. Wilt does not see significant improvements as evidenced by the pink and purple line relative to the green line. However, with the Wilt-BERT model, we see that the continual learning algorithms of sequential fine-tuning and experience replay help the SST2 task, which is seen by the green and orange line compared to the blue dotted line. We see that the visual common sense reasoning tasks again hurts transfer here. And we also observe that continual learning hurts multi-choice tasks like HelloSwag and Pika. In conclusion, we propose Climb, a benchmark to study continual learning in multimodal settings. Climb is designed as an extensible community tool for studying tasks, model architectures, and continual learning algorithms. We see that existing continual learning methods, which are designed in unimodal settings, fail at generalizing well to sequences of multimodal tasks, and there's a need for new research into continual learning strategies for this challenging multimodal setting. Thank you.